Hello again. This is Math 2-115 coming to you from the College Edu page. The title of this lecture is Algorithms. And as always, please be an active learner as you watch this video. An algorithm is a finite sequence of precise instructions for performing a computation or for solving a problem. Okay, so there are many ways to describe an algorithm. Here we describe an algorithm for finding the maximum largest value in a finite sequence of integers. And we can do this in a narrative fashion. And so here are the steps. Set the temporary maximum equal to the first integer in the sequence. The temporary maximum will be the largest integer examined at any stage of the procedure. Compare the next integer in the sequence to the temporary maximum, and if it's larger than the temporary maximum, set the temporary maximum equal to this integer. Repeat this step if there are more integers in the sequence. Stop when there are no integers left in the sequence, and the temporary maximum at this point is the largest integer in the sequence. Here we use some pseudocode to describe it. Pseudocode looks like many languages, Java, C++, and things like that, but without the rigorous syntax. So here's an algorithm for finding the maximum. So the procedure is, and this is the name, given input as integers, you want to find the maximum of in integers. So you set the max and you do an assignment. So the value A1, which is the first integer in the sequence, is assigned to max, and for I equaling 2 to n, you check, and if the max is less than ai, the next one you're doing, whatever value I is, then you assign ai to be the max, and then you do that over and over again until you've done all of them, and then you return the max, and max is the largest element in that set. So this is an example of an algorithm that is coded in pseudocode. Now, algorithms have several properties, and they're useful to keep in mind. And the properties are: there is input, there is output. The steps of the algorithm must be defined precisely. The algorithm should produce correct output values for each set of input values. The algorithm is finite. It produces the desired output after a finite, perhaps large, but a finite number of steps for any input in the set. It must be possible to perform each step in an algorithm exactly and in a finite amount of time in order for the problem to be finite, and the procedure should be applicable for all problems of the desired form, not just for one particular set of input values or a particular set of kinds of input values. The general searching problem can be defined as follows. Locate an element X in a list of distinct elements A1 through AN, or determine that it's not in the list, and we could say it's not there too. So the solution to this problem is the location of the term that equals X, or put 0 if X is not in the list. There are many different kinds of searches. The linear search is the first algorithm we'll discuss, or this is also called the sequential search. The linear search algorithm begins by comparing X and A1. And if X is equal to A1, that is the solution, namely it's in position 1. If X doesn't equal A1, we then compare it to A2, and if X equals A2, that's the solution. If that's not there, we continue on through this, comparing X successively with each term in the list until a match is found, where the solution is the location of that term, unless no match occurs. If the entire list has been searched without locating X, the solution is 0. Here is pseudocode for this, and you should understand that the pseudocode works. So we're doing a linear search across these distinct integers. So we start with I being assigned 1. While I is less than or equal to n, the number up here, and xi does not equal a sub I, then you advance I and you continue. If I is less than or equal to n, then the location is equal to this. That is, if we finish this loop and have an answer. Else, the location equals 0. and that returns the location. So either you found it or you didn't. And you could code this in many languages if you paid careful attention to the syntax. We now consider another searching algorithm. This algorithm can be used when the list has terms occurring in order of increasing size. For instance, if the terms are numbers, they are listed from smallest to largest, and if they were words, they'd be listed in alphabetical order. And this is called the binary search algorithm. It proceeds by comparing the elements to be located to the middle of the list. The list is then split into two smaller subsets of the same size, where each smaller list has fewer terms than the other. The search continues by restricting the search over and over again based on comparison of the element to be located and the middle term. And this is very much more efficient than the linear search. In a later section, we will talk about how it is, but let's see how it works right now. Okay, so we're searching for 19 in this list. Well, the first thing, we split it into half. And you see, we know the biggest number here is 10. So if we're looking for 19, we throw all of these away and we just look here. But then we split this list into half again. And we can see that the biggest one here is 16, so I don't have to look there anymore. So I look only over here. And then I split this list in half, and it is here. Now, what happens is when I look into this, I know I'm going to look here. I can throw this away, and eventually I find the 19. Now, we can't specify the steps of the binary search algorithm, and in fact, here it is in pseudocode. So the procedure is the binary search. Your input are the numbers, and those are in increasing form always. You start with I equal 1, and then what you do is for every I less than j, you go through. Now we do a comparison here because the search is restricted to a list of no more than, and this is the smallest integer greater than or equal to x. That's what this symbol means. We've talked about this before, and so you've restricted it that way. So we go through and we do the comparison, and if x is greater than am, then we can do this assignment statement. Otherwise, we leave it as m. And at the end, if we found AI, then we know location, we can report it. If we didn't find it, but we've exhausted all the possibilities, we return 0. A much more efficient search than a linear search. An amazingly large percentage of computing resources devoted to sorting one thing or another. You might remember that that was the first step in doing the binary search, was having things sorted. So much effort has been devoted to developing sorting algorithms, and we're going to talk about that. In this fundamental work, The Art of Computer Programming, this computing maven has 400 pages devoted to sorting, and there are more than 100 sorting algorithms that have been developed. And there are new sorting algorithms being developed all the time. One of them that we will talk about is the sorting algorithm that is called the library sort, also called the gapped insertion sort. We'll talk a little bit about this. And the reasons why people study this is they want to have easy implementation, but they also want them to be efficient, either in general or at least for certain kinds of problems. And so many algorithms take advantage of particular computer architectures, and some are very clever. We're going to talk about two sorting algorithms here, the bubble sort and the insertion sort, and I will make conceptual reference to the gapped insertion sort. The first one that we're going to talk about is called the bubble sort. It is one of the simplest sorting algorithms, but not one of the most efficient. It puts a list in increasing order by successively comparing adjacent elements, and if they are in the wrong order, you interchange them. To carry out the bubble sort, we perform the basic operation, that is, interchanging a larger element with a smaller one, beginning at the beginning of the list, and we go through a full pass. We iterate this procedure until the sort is complete, and there's some pseudocode given here as well. We can imagine the elements in this list placed in a column, And in the bubble sort, the smaller elements bubble to the top, and the larger elements sink to the bottom. And this is illustrated with an example down here. Let's suppose that we started here. So we began, and so the first pass we go through, since 2 is smaller than 3, we exchange those. Now we compare the next two, and that is in the correct order, so we just leave that alone. So we go to the next one, we compare those, and we switch that, and we get this as an order. And we compare the last two, and we'll say there, we've completed one pass. But now you see what we've done is we do have the 5 at the bottom. Now we do the second pass. So we start at the top, and we compare. Those are in a good order. We go here, we have to switch them. And if we go down here, we're good, and the 5 is locked in. So we go to the third pass. Here we look at it again. Here we switch that, and by this time we're where we need to go. But the fourth pass, what we see is we check and we see we're finished, and that's the steps of the bubble sort. And here is the procedure written in pseudocode as an algorithm, and you see it is nested do loops. And again, you should be able to code this in your favorite coding language, but you will pay attention to syntax. Another fundamental type of sort is called the insertion sort. The insertion sort is a simple sorting algorithm, but again, it's not the most efficient. To sort a list of n elements, the insertion sort begins with the second element, and it compares the second element with the first element, and it inserts it, that is, the second element, before the first element if it does not exceed the first element, and after the first element if it exceeds the first element. At this point, the first two elements in the set are in the correct order. The third element is then compared with the first element, and if it's larger, you go down and you do this. And so it is inserted into the correct position among the first three elements. In general, in the ith step of the insertion sort, the ith element of the list is inserted into the correct position in the list of the previously sorted j-1 elements. To insert the jth element into the list, a linear search is used. So you see you're using these search techniques together, and so you compare them and you do the insert. Okay, so here is an example of the code doing an insertion sort. And here is actually an example of taking this list and doing it in increased order. So the insertion sort first compares the 2 and the 3. Because 3 is bigger than 2, it places 2 in the first position. And so now we have this list. And the colored part is what's been sorted already. At this point, 2 and 3 are in the correct order. And next it inserts the third element, 4, into its already sorted part of the list. Because 4 is bigger than 2, 4 is bigger than 3, and this remains in the third position, so now we have it sorted here. Now we move to the 1. Next we find the correct place for the 1 among the already sorted elements. Because 1 is less than 2, and so on and so forth, we obtain this list, and eventually we insert the 5 at the correct position at the end. So again, an insertion sort is a different kind of sorting algorithm, and notice it at its heart includes a linear search technique as well. In closing, now more than ever, time is precious. Each day must count. Do the math. It'll make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all. More later and soon.